Okay, so we are continuing the notes from 5.2 that we started in class. So remember, we did the Patty paper and we were constructing things and we found the circumcenter and the incenter. So what we're going to do with this now is we're going to look at theorems that involve circumcenter and incenter and help us deal with measurements and information about the triangles themselves. So take a look at the first diagram. Let's look at the circumcenter theorem. So remember, what makes a circumcenter a circumcenter? Remember, it's the point of concurrency of the three perpendicular bisectors of a triangle. So just to remind you, when we're talking about perpendicular bisectors, you're looking for the segments that are perpendicular to each side and cut each side in half. So where these three pink highlighted segments meet, that's your circumcenter P, right? So just remember, P is your circumcenter. Excuse the bad handwriting, but again, P is the circumcenter. And again, we know that because those pink highlighted lines are your angle bisectors, okay? So now what do I know if we have a circumcenter in a triangle? Well, let's write down the theorem. All right, so our circumcenter theorem says that the circumcenter of a triangle is equidistant from the vertices of the triangle. So I'm going to make sure we write that down. Pause if you need to, so you can listen when you're ready. But again, the circumcenter of a triangle is equidistant from the vertices of the triangle. So remember, those pink segments showed us where the circumcenter is. So now once I have my circumcenter, what I'm going to look at is I'm going to look at the distance from the circumcenter to the vertex from each of the corners of the triangle. So if I know P is the circumcenter of, this is triangle ABC, that's given, then what I can conclude is that the distance from P to each angle, so PA, is going to be the same as PB, which is going to be the same as PC. So that's what equidistant means. And that is your circumcenter theorem. Okay? Let's go ahead and use that circumcenter theorem for our first example. All right, I just realized I forgot to type in something earlier, so we're just going to mark this in and pretend this was here all along. But we should know that DG, EG, and FG are perpendicular bisectors of the triangle. So let's just go ahead and mark this in. So we're going to know that, again, we've got perpendicular bisectors. So sorry about that. Pretend that was already printed for you. All right. So we've got these perpendicular bisectors. So that means each half of the side, each side is cut in half, right? So the halves are equal. And then we've got these perpendicular lines. So we've got these right angles. All right. So remember, what does this tell us if we're trying to find the measure of, for example, BC, right? Well, since we know G is what point? Well, you should see G as the circumcenter. Because DG, EG, and FG are perpendicular bisectors, right? And G is the intersection of those three. So since G is a circumcenter, then the circumcenter theorem tells us that GB is equal to GC, which is equal to GA, because the distance from the circumcenter to each vertex is going to be the same. So since we know that GB is 13.4 based on diagram, we know that GC should also equal 13.4. And again, remember, the answer is not the biggest issue. It's the logic that helps us get there that I think is the most important. All right, let's move on to example 2. So how will we find a circumcenter graphically? So let's first plot some points and make a triangle. And let me just write the directions really quick. So we are going to find the circumcenter. Write that a little more clearly. Of the triangle. All right, so let's go ahead and plot some points to make us a triangle, and then we'll work through this problem. All right, so there's our triangle HJK. So H is at 0, 0, J is at 10, 0, and K is at 0, 6. So what we need to do is we need to find the circumcenter of this triangle. And remember, to find the circumcenter, right, the circumcenter, we need perpendicular bisectors. So we need to find where perpendicular bisectors intersect. So we need to basically find two perpendicular bisectors and their point of intersection. And that's how we're going to find the circumcenter. So what's really great about this triangle is that it's a right triangle. And remember, it's a right triangle because it's right here at the origin, and we've got a leg on the x-axis and a leg on the y-axis. And this makes finding a perpendicular bisector super easy, because if we've got a horizontal line, I can cut that in half, no problem, right? I can just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, divide that by 2, and know that here is the midpoint, right? And then since this is a flat line, my bisector should just go straight up and down. I know my line's a little crooked because I was sketching that in, but again, this is your perpendicular bisector of HJ, right? And that's the line x equals 5. It's x equals because it's a vertical line, right? So there's one perpendicular bisector. Then I need to find a second one, and that is going to help me locate the circumcenter. Let me use a different color here. All right. So again, vertical line, super simple to cut in half. So it's 1, 2, 3, 4, 5, 6. That's the length divided by 2, and I know the midpoint is here at y equals 3. And if I just extend that horizontal line here in orange, that's my perpendicular bisector of KH. That's going to be y is equal to 3. And again, it's y is equal to 3 because it's a horizontal line that goes through the value of y, which is 3. And that point of intersection is going to be my circumcenter. So right here where they meet, I'm highlighting right here in pink, this is the circumcenter. Right? And that point is the point 5, 3, and that is my answer. So super easy when you have horizontal and vertical lines. If you don't have a right triangle, then remember, go back to our notes from the other day in class, the 5.1, and write the perpendicular bisector equation and graph it or solve a system. All right. And then if we have problems that come up like that, please don't hesitate to ask in class. But again, if you have flat lines, horizontal, vertical, just cut them in half and go for it, just like example 2. All right. Moving on to the incenter. So this is our second point of concurrency in section 5.2. And remember, the incenter is created from the angle bisectors. So I know the diagrams can look very similar because you'll notice, wait, we have right angles and all this, but remember, you have angle bisectors, the incenter, right? Moving up, if we have segment bisectors, that means these sides are cut in half, then it's a circumcenter. So you're going to want to make sure you see those little differences because we're going to have a lot of diagrams that all involve triangles in this chapter. Okay, so again, let me just highlight that again. We know that P is the incenter of triangle ABC here because it's where those angle bisectors, which I will highlight here in yellow, AP, BP, and CP all intersect at P, right? Those angle bisectors intersect at P. All right, so let's write down our incenter theorem now. All right, so our incenter theorem is very similar to the circumcenter theorem. So remember, you want to make sure you see which point of concurrency we have in the diagram before you rush and make any conclusions. But the incenter of a triangle is equidistant from the sides of the triangle. So if we go back to what we're given here, right? P is the incenter of triangle ABC. Then I can conclude that P to each side, so PX is equal to PZ, which is equal to PY. And we tend to use this right angle because we like looking at the shortest distance from side to side, okay? So again, PX, PZ, and PY are all equal because P is the incenter. Be very careful. Notice how Y is not the midpoint of AB. Z is not the midpoint of BC. X is not the midpoint of AC. We don't know it's a midpoint unless we've got a circumcenter. So please be aware of that. Okay? One final example, and I am done for today. Let's look at example 3. We're going to use our point of concurrency here to find some values. So here's what we're going to do. All right, so first we're going to talk about the distance from P to MN. So if you take a look at the diagram very carefully, you want to think about what we're given, right? And in this diagram, we are given, oops, I forgot to write this down again, so sorry about that, my bad. We would know that PM and PL are angle bisectors of triangle MLN. Sorry about that, typos everywhere. So we're given that information. PM and PL are angle bisectors of triangle MLN. So taking a look at that, what's given to us there, that tells us P is what point of concurrency? We can conclude P is the incenter. Right? So if P is the incenter, then I can use the Incenter theorem. Say that, well, P is equidistant. All sides of triangle all sides of triangle MLN. All right, just going to scoot down a little bit here. And since we already know that the distance from P to ML is 5, that means the distance from P to MN is 5 as well. Right? Sorry about that, that's just is. Okay, because we already know that the distance from P to ML is 5, then the shortest distance from P to any other side should also be 5. Okay, so that's your Incenter theorem. B takes a little bit more work because we're calculating the angle PMN. But take a look at what you're given. You are given, this angle is 20 degrees. All right, we're given this angle over here, which is 50. So let's think about what we know about triangles. So think back to chapter 4. What do you know about angles inside a triangle? Remember, angles in a triangle sum to what number? 180 degrees, right? So that means the measure of angle N plus the measure of angle MLN, let me name that a bit a little better, MLN plus the measure of angle LMN should add up to 180 because those are the three angles of your triangle, right? So I already know that the measure of angle N is 20. I know that this angle is 50, this PLN, but that's not the entire thing, MLN. But we know that PL is an angle bisector, right? Which means if this is 50 here, what would the angle measure MLP be? Well, that should also be 50. So that means this entire thing is 100 degrees, right? So now I can substitute to solve for the measure of angle LMN. So here, 20 plus 100 plus the measure of angle LMN should equal 180 degrees, right? Solving for the measure of angle LMN, right? Adding 20 and 100 to get 120. Taking away that from 180, I should get 60 degrees. Now notice this is not PMN. So now let's back up and say, well, if I know LMN, which is this angle right here in green, let me erase some stuff so it's not as confusing here. All right, there you go. So again, if we know that LMN now is, this whole thing is 60 degrees, and I'm looking for just PMN, which is this one right here, how much of PMN is LMN? Well, we know again it's an angle bisector. So that then I know that the measure of angle LMN is 2 times the measure of angle PMN, right? So then I can just divide 60 by 2. And then I know that the measure of angle PMN is 30 degrees. So here I used a combination of the idea of the incenter, the definition of incenter, with my definition of bisectors, right, to help me figure out the angle measures using the triangle sum theorem. Okay? So definitely going to practice this in class. Please come back with questions. Let me know if you couldn't read something, if I'm going too fast. I want to make these videos work for you. Feel free to watch it again if you need to go back and review. And I'll see you in class.